AB Calculus, Section 4.1, Maxima and Minima. Let's first talk about a definition, the absolute maximum and minimum. Let f be defined on a domain, D, containing the point x equals c. If f of c is greater than or equal to f of x for every x in that domain, then f has an absolute maximum value of f of c on that domain at x equals c. If f of c is less than or equal to all values of f of x within that domain, then f has an absolute minimum value of f of c on that domain at x equals c. Absolute maximums and absolute minimum values are called absolute extreme values, which refers to either of those two. A definition written in a similar way: suppose that c is an interior point of an interval I, on which f is defined. Now we're taking this set D, which we didn't necessarily have endpoints on, could have possibly been an infinite interval, right, where there's no limit to the right end or the left end, but now we're going to limit that right end and left end and call this interval I. Same definition: if f of c is greater than or equal to f of x for all x in I, then f of c is a local max. If f of c is less than or equal to f of x for all values in I, then f of c is a local minimum. So there are two conditions that we need in order for an absolute maximum and an absolute minimum to exist. First of all, the function, let's say f of x, it must be continuous. And the other is that the function exists on a closed interval. Okay, it can't be an open interval, it's got to be a closed interval. Okay, so let's talk about this theorem, the extreme value theorem. This is absolutely 100% a theorem that you're going to want to be comfortable with. This is knowledge that you will need for the exam in May. All right, let's talk about it. This is also called the Min Max Existence Theorem, a function that is continuous. That's part one of our two-part checklist for this theorem. On a closed interval from a to b, function exists on a closed interval, has an absolute max value and an absolute min value on that interval. It's going to happen. There will be an absolute max. There will be an absolute min. So as we look at the graph of a function, right, let's look at this graph here. Now this graph is continuous, but it's not differentiable. You can see that this point right here at x equals e is not differentiable. However, the function is continuous on the interval from a all the way over to b. We can see clearly that our absolute minimum value is here at f of a. Our absolute max value is here at f of e. There are local maxima and minima along the way. However, of course, this function satisfies those two criteria, that the function is continuous and it exists on a closed interval. Therefore, we can locate the absolute minimum and the absolute maximum value. So the theorem, the local extreme point theorem, if f has a local max or min at c and f prime at c exists, then f prime at c must be 0. Okay, so if f has a local maximum or minimum value at c, so let's look here. We got a local maximum value here. We got a local minimum value here. We got a local maximum value here. And it's within the interval, not on an endpoint, right? The derivative will not exist here at the endpoints of this interval. Okay, which of the following points C, D, and E satisfy the local extreme point theorem? Well, f prime exists at two of the three locations: f prime at C, f prime at D, f prime at E. Okay, does f prime at C exist? Yes, it does. It's 0. Does f prime at D exist? Yes, it does. Therefore, it's got to be 0. Does f prime at E exist? No. Therefore, the derivative there does not exist. Okay, so if you have a local minimum or maximum value and the derivative exists at that point, the slope at that point must equal 0. All right, let's continue with a few examples finding absolute minima and maximum values. All right, in order to find absolute extreme values on a closed interval, the first thing we got to know is how to use what's called a critical point. An interior point C of the domain of f at which f prime at C equals 0 or it fails to exist is called a critical point. Okay, these are going to be some of the potential candidates for an absolute minimum or maximum value. The other candidates will be the endpoints. So the steps for locating absolute extreme values. Assuming f is continuous and on a closed interval, these are our 3 steps. Locate the critical points. These points are candidates for absolute min and max values. Then we're going to evaluate f at each of the critical points as well as the endpoints a and b. Then we choose the largest and smallest values of f from step 2, and these are your absolute extreme values. Let's take a look at an example below. Find the absolute maximum and minimum values of the function below. All right, so first of all, I'm going to put our candidates over here to the side. And the candidates consist of 2 items. Our critical points and our endpoints. So our endpoints we already know. X equals -2 and x equals +2. Our critical points we got to do a little bit more work for. So our critical points are where f prime of x either equals 0 or f prime at x equals an undefined value where it does not exist. Now, the derivative of this function is a polynomial, therefore we're actually not going to have to worry about the derivative not existing. So we're going to simply be working in this case where the derivative equals 0. So let's find f prime at x. F prime at x will equal 4x cubed minus 6x squared. Clearly this polynomial will exist everywhere, so its domain would be all real numbers, so we won't have to worry in this case, like I mentioned earlier, about the derivative not existing. That will not be an issue. So now we set the derivative equal to 0, and we solve the polynomial in our traditional methods. So in this case, I'm going to factor. I'm going to pull out a 2, and that will leave me, I'm going to pull out a 2 and an x squared. That will leave me with a 2x minus 3. It looks to me like if we use the zero product property, and I set these 2 factors equal to 0, that I would get x equals 0 and x equals 3/2. Okay, so now I have my critical point, x equals 0, x equals 3/2. Now, when I consider these, I do want to consider that the critical points have to be values that fall within the interval, and both 0 and 3/2 fall within the interval. Therefore, I'm going to check all 4 of these values. I'm going to take f of x, and each of these values, I'm going to find outputs. Okay, so I'm going to take a -2 and a 0 and a 3/2 and a +2. I'm going to plug them into f of x. When I do so, f of -2 equals 32, f of 0 equals 0, f of 3/2 comes out to be -1.6875, and f of 2 equals 0. So in this case, I have an absolute max at f of -2, which equals 32, and I have an absolute min. At f of 3/2, which equals negative 1.6875. Okay, I identify those by the largest possible output and the smallest possible output. So I've got my minimum here, I've got my maximum here. All right, let's continue with another example. Alrighty, example 2. This is an AP style problem, no calculator allowed. The function f is defined by f of x equals natural log of x over x for all x greater than 0. The maximum value of f on the interval 1 over e to e is, okay, so at this point, when you're looking at this problem, you should see maximum value. That should make you think max min existence theorem, right? And the first thing you should think in your head is continuous and closed. So I see the closed interval here. That closed interval exists within the domain of the function, x greater than 0. Therefore, check on both of those. Okay, so I want to look at my candidates here. My candidates are going to be my endpoints and then critical points. Well, my endpoints are x equals 1 over e and x equals e. My critical points, I got to do a little work to find. So I'm going to find f prime at x. Okay, f prime at x. I'm going to have to use the quotient rule here. So I'm going to take the low function times the derivative of the upper minus the upper times the derivative of the low function, all divided by low squared. Okay, so I want to know where f prime at x either equals 0 or f prime at x does not exist. Okay, so let's determine where that would be. So let's simplify f prime at x first. F prime at x simplified would be 1, which is x times 1 over x, minus ln of x over x squared. Well, where would the derivative, f prime of x, be non-existent? Well, that would be at x equals 0, right? Which I'm not necessarily worried about because that's not within my interval from 1 over e to e. So f prime at x does not exist at x equals 0, which is somewhat irrelevant because I'm being told right now that x only exists, the function only exists when x is greater than 0. Okay, so I want to know where f prime at x equals 0. So we're going to work this out by taking 0, setting it equal to 1 minus ln of x over x squared. And the only way that 1 minus ln of x over x squared could equal 0 is if 1 minus ln of x equals 0. You could think of that as cross-multiplying, or you could just determine that the denominator can never equal 0. Therefore, the only way that equation could equal 0 is if 1 minus ln of x equals 0. Okay, so that means that in order for 1 minus ln of x to equal 0, ln of x has to equal 1. And the only way that happens is if x equals e. Okay, so our critical point is x equals e. All right, so really, in essence, right now, because my endpoint is equal to one of my critical points, I only have to check 2 values. So I'm going to take x and f of x, and I'm going to check 1 over e and e. Whichever one of those is larger as an output, we will use as the max value. So f of 1 over e will equal ln of 1 over e over 1 over e. Okay, and f at e will equal ln of e over e. All right, so let's think about this logically. Ln of 1 over e. I'm not allowed to use a calculator here, so I got to do some work with this. This is the same as the natural log of e to the negative 1. All right, And what that comes out to be is -1. Therefore, f of 1 over e comes out to be -1 over 1 over e, which is -e. Okay, now let's find f of e. Well, natural log of e is 1, so 1 over e is exactly that, 1 over e. Now, which of those is larger? The positive one is going to be larger. Therefore, our max value is going to be c, which is 1 over e. Okay, you want to be careful to make sure that you don't identify e as your max value. That is the input for your max value. This is your max value, 1 over e. All right, let's do another example on the next slide. All right, example 3, AP problem from back in 2007. This is a non-calculator example. So yet again, we're going to have to rely upon, it looks like, some trig and maybe some special algebra skills here to find the answer. So let's read it. A particle moves along the x-axis with position at the time t given by the following for the time from 0 to 2 pi. Part A of this particular question said find the time t at which the particle is farthest to the left. Okay, so anytime you see farthest and to the left, you should think max-min existence. And in this case, you should think I'm looking for a minimum value, right? Left helps you to recognize a minimum value. Farthest tells you absolute. Okay, so let's justify our answer in a moment here with our work. Okay, so our candidates, of course, are made up of our endpoints. Endpoints in this case are t equals 0 and t equals 2 pi. Our critical values we're going to find by finding x prime of t. Okay, so x prime of t. We're going to have to use a product rule here. So the derivative of the first would be -e to the negative t. We leave the second alone. Derivative of the second would be cosine of t, and we leave the first alone, e to the negative t. What I want to know is where that either equals 0 or does not exist. Now in this case, x prime at t will exist, okay? So we are not going to have to worry about this not existing. Okay, very similar to a previous question. Okay, so since it will exist for all values, and you'll see why here in a minute, I want to know where it equals 0. So I want to know where x prime of t equals 0. So let me write this out. Oh, that was poorly written. Let me retry. Retry. That shows you right there that I am a math teacher. Okay, so I'm going to set this equal to 0, and I'm going to do some work on this. I'm going to factor out an e to the t. Okay, so if I e to the negative t, that will leave me with negative sine of t plus cosine of t. So I'm actually going to write that as cosine of t minus sine of t. All right, so now I have two factors, my outer factor, and this binomial here. Actually, it's not a binomial, it's just a expression with two terms. But what I want to do is set each of them equal to 0. Okay? And cosine of t minus sine of t also equal to 0. All right, now this expression here, this exponential function cannot equal 0. It will never be equal to 0. All right, so this will yield us no solution. However, on the other side, I would want to find where cosine of t and sine of t are equal. Okay, so within the confines of 0 to 2 pi, where are the cosine and the sine the same? Well, if I were to look at the unit circle, all right, at my pi over 4 locations, right, at pi over 4, at 3 pi over 4, at 5 pi over 4, and at 7 pi over 4, sine and cosine have the same value, but some of their signs vary, right? One is positive, one is negative. Let's determine which ones will work for us. Well, in quadrant 1, we get positive sines and cosines. So sine and cosine would be equal there. In quadrant 2, we get negative cosine, positive sine. So 3 pi over 4 isn't going to work for us. Okay, at 5 pi over 4, I've got negative cosine and negative sine. That will work for us. And in quadrant 4, I get positive cosine, negative sine. That will not work for us. Therefore, at t equals pi over 4 and 5 pi over 4, we would have what we would consider critical values. Okay, so t equals pi over 4 and 5 pi over 4. Okay, so now let's test these within x of t. So let's test our t values within x of t. All right, so we're going to test 0, pi over 4, 5 pi over 4, and then 2 pi. I'm guessing there's a couple of gimmies here. Sine at 0 is 0, so that would make x at 0 also 0. Sine at 2 pi is also 0. That'll make x at 2 pi also 0. Okay, so pi over 4. What is the sine of pi over 4? Well, I know it's greater than 0, right? So e to the negative pi over 4, that's also greater than 0. So I'm going to get a positive value here for x of pi over 4. Okay, now sine at, let's see here, 5 pi over 4. Well, that's less than 0. And e to the negative 5 pi over 4, that's also less than 0. Excuse me, that's greater than 0. So I know that x of 5 pi over 4 will be negative. Now, without even finding the value, I've already found the time, the time when the particle is furthest to the left. Why? Because x prime at t, that's the only value where its output or its location is less than 0. Therefore, the particle is farthest, I'm abbreviating, I'm running out of space, to the left at t equals, what would that be? Oh yeah, 5 pi over 4. I don't think there's units for time, so we're just going to say 5 pi over 4. Okay, that is my justification. Okay, I don't need to actually have the location or the minimum value, right? I don't need to have that. It just asks what time. All right, let's look at one more example. Okay, I might have told a fib. 2 more examples. Example number 4, AP problem. And guess what? We get to use our calculator. So I'm going to get my calculator out. I'm going to make sure I'm in radian mode, which I am. Okay, make sure my batteries are good to go. Who uses batteries anymore? Let f be the function defined by f of x equals natural log of x plus 1 minus sine squared x for the interval 0 to 3. Find the absolute maximum and absolute minimum value of f and justify your answer. So your work will be your justification. Our candidates. Okay, endpoints. So we'll keep our color code going here. Our candidates will be x equals 0, x equals 3. Those are our endpoints. Now we got to find our critical values. So I'm going to put f of x in for y1 in my calculator. Okay, now I'm going to teach you a little bit about how to use your calculator here. We've already done a little bit of this using Math 8, but I'm going to type in y1 is ln of x plus 1 minus sine squared x. So if you haven't done that yet, go ahead and type that into your calculator. Okay, the next thing that I want you to do is in y2, I want you to press math 8. And then within that, I want you to do this. I want you to pay special attention to my notation here. y2 is going to be the derivative of y1 when x equals all x. Okay, and then we're going to graph this. Now within our window, I'd like your window to be an x minimum of, let's go 0. Let's go x max of 3. Now I picked those numbers specifically based on this interval. You can go a little wider than that just in case you get a little paranoid. Your y min and y max, I would just make sure, I don't know, let's go -1, y max, +1. Why did I choose 1 and -1? Just so that I can see where the function is going to cross at 0, if it does at all. Okay, and then where it crosses, we will be able to call our critical values. Okay, let's do that. So go ahead and graph, and let's sketch the graph below. Okay, so here's a graph of y2. Okay, this is the derivative function. Okay, so this is equal to f prime at x. Okay, so let's define that real quick. Got to make sure that we tie these together. y2 is equal to f prime of x. Okay, so the sketch of y2 is going to look like this. Okay, it looks like I've got, I'm going to estimate here, okay, from 0 to 3. Looks kind of like, oops, goofed that up. Let me see here. Kind of goes above this window and then comes back down like this. Okay, so within my intervals here, I've got 1, I've got -1 for my y value, and then I go from x equals 0 out to x equals 3. So my critical values that I'm going to want to be aware of are right here and right here. So I'm going to call this point A, and I'm going to call this point B. All right, so I'm going to find those values by pressing math, make sure you're on your graph, press second trace, and then I'm going to go with option 2, which is 0. Okay, so option 2, I'm going to make sure that I'm on the correct function. Okay, and then I'm going to use a left bound. So a left bound on that first value. Press enter. Right bound on that first value. Press enter. And it tells me that A, this value here, comes out to be 38985. Now I'm going to store this, and how you do this, okay, is immediately after you press enter the third time, because it asks you for left bound, right bound, guess. Once you press enter for guess and it gives you that answer, it is storing that x value into your calculator as the previous answer. So go to your home screen and press second answer or second negative symbol, and it'll pull that value 0.398388985. And I want you to press stow, which is down near the on button, and alpha and the math button, which will store it as A. Okay, so now what we've done is we've done stow alpha A. Okay, so now A is equal to that value. We're going to use that in just a minute. It's going to help with our calculator. So let's go with x equals, and we can abbreviate this right now, not using in our calculator in a minute, but we'll go out to 3 decimal places for just a minute. and write that x equals 0.398. Now let's find the other critical value right here. So we'll do a left bound, right bound, guess. It'll give us our value for b. Okay, I'm getting that b equals 1.351. Okay, so x will equal 1.351. I'm going to stow that as b. Okay, so b is going to be 1.351 and some change, 1348. All right, I'm going to do a little stow b for that value, and then we're going to test these values in just a moment. Okay, so when you want to stow b, you press stow and then alpha and the apps button. Right above the apps button is a green b. Okay, so now we got to go back to our function, and we got to test each of these values. So here's our x values and our outputs. Okay, so here's where you want to use your calculator. Okay, the alpha trace will bring up your function value, which is y1. So we want to do y1 of 0, y1 of point, well, actually let's call it a, y1 of b, and y1 of 3. Okay, so our values, if we use 0, 0.398, 1.351, and x equals 3, we get outputs of 0. Our calculator for y1 of a gives 0.185. Output for b would be negative 0.0976 or 0.98. And output for 3 is 1.37. Oops, excuse me, 3 decimals out would be 1.366. Okay, so it asked for the absolute maximum value. The absolute maximum value is located at f of 3, which is equal to 1.366. And the absolute minimum value, that's an interesting yellow, would be f of 1.351, which is equal to negative 0.098. All right, guys, let's look at the last example for these notes. 2008 multiple choice. All right, let's read it. The function f is continuous between negative 2 and 2, such that f of negative 2 is equal to f of 2, which is equal to 0. Let's make a quick sketch. All right, so in the interval from negative 2 to 2, we know that the output at the endpoints is 0. So each of these points, 2, 0, negative 2, 0. Let's read the rest of the question. If there is no c, where c is between negative 2 and 2, for which the derivative equals 0 at c, which of the following statements must be true? All right, so let's look at a sketch of part A. Okay, so if I go from negative 2 to 2, if on the interval from negative 2 to 2, the derivative is greater than 0, okay, so the derivative is always greater than 0, well, that's a problem, right? Because then I would have a discontinuity there. Okay, so that's an issue, right? Because f is continuous, so that's out. Okay, part B, very similarly, part B would take, let's do part B in blue on the same graph. And if the derivative between negative 2 and 2 such that the derivative is less than 0 for all values, well, actually I gotta resketch that. Let me try that again. Since this slope always has to be less than 0, well, again, I've got a discontinuity there, right? Because the output at 2 has to also equal 0. Okay, let's see, the derivative can't equal 0, but for part C it says the derivative always has to exist. Well, is there a way for me to draw a function, right, such that I can go, let's go in green here for C. Well, let's see. I'm going to go from 0 at -2 and then come back. Well, that's a problem, right? Because right here, f prime at some value k equals 0. That's an issue, right? I can't do that, right? Because that's part of the problem itself, is there's no value where the derivative equals 0. Okay, so C is out. How about part D? Let's do D in yellow. For a k value between -2 and 2, the derivative exists, but f prime is not continuous. That actually is in direct conflict with its own comment. F prime at k cannot exist and also not be continuous. Okay, so that's going to be out just because of the dichotomy going on there. Therefore, E, for some k, where k is between -2 and 2, f prime at k does not exist. So let's sketch that right over here. We're going to go with a purple here. Yeah, that looks good. Okay, so if I'm to have an output of 0 here and an output of 0 here and never have a derivative of 0 somewhere in between, I would have to have a value, right, a value k such that f prime at k does not exist. That's the only way that I can achieve everything that this question is asking for. All right, guys, that is 4.1, day number 1. We'll see you in the next video.